Computers are fascinating machines, and their ability to perform mathematical calculations at stunning speeds help us to solve complex science and engineering problems in a way that was impossible using conventional pen and paper approach. If you are curious about how these simulations are developed and want to get an intuitive understanding of its core concepts, keep watching because in today's and some upcoming sessions, I'm going to take you to the fascinating world of physics through the language of computer simulations. I'm Vaishak. Welcome to Physics, Code, and Animation.
Hey, welcome back. Glad that you want to learn further and explore the world of simulations more. This is the second part of the series where we will improve our simulations of the bouncing ball. If you are here for the first time, please pause the video and watch the first part of the series where we started the model from scratch. In the previous session, we explored the equations of motion, how to use the concept of approximate derivatives to write equations that progress in time, how to simulate bounds, how to model energy loss, avoid some numerical instability, and how to validate our results. In today's session, we will see how the same program can be rewritten in a more structured way using classes and functions in Python. Thus, our simulation will become reusable and can be imported into other programs for visualization and post-processing. Today's session is going to be a bit more programming heavy than the previous one. So if you are a total beginner to Python, take some time to brush up your Python skills. I will try to explain the concept of classes and functions as clearly as possible, but these are foundational concepts in programming, and it is better to learn them in a very systematic way. So let's get started. This is the final version of the code we wrote last time. It works fine, gives good results, and it is very easy to read also. So why do we need to change it? Imagine a condition where you want to simulate 10 balls with different parameters. Our current script requires running it 10 different times or making 10 copies of it, which is not ideal. Reusing this code in another project as part of a bigger simulation requires copying everything, making the main code bulky and harder to manage. Also, any future update to the ball model would also need to be copied manually to the main code every time. Over a period, this becomes frustrating, error prone, and makes your code messy and unreadable. Fortunately, most programming languages allow writing codes that can be reused. Here, large programs are split into multiple blocks that represent a physical system component. Each block can be written separately and then can be called into other blocks. This approach is called object-oriented programming, and the concept of classes form the foundation of this approach. Let's take a look at our program. Our simulation can be represented using three main components. The ball, which updates its position at each time step, and this ball component interact with the world component to check for collision with the ground, and then it performs a bouncing action. Meanwhile, the observer tracks the time, position, and velocity of the ball for analyzing and plotting. Before we build our simulation in this way, let's briefly discuss functions and classes. Functions group a set of instructions into a single command, making code reusable and cleaner. For example, updating the velocity and position in each time step can be bundled into a move function. Once defined, we can call it any time without rewriting the logic. In Python, a function starts with a def keyword followed by its name and input parameters within parentheses. The function body contains the logic and it optionally can return a value back to the main code. Thus, the user does not need to understand the underlying logic to use the function. Classes in Python let us group related data and functions into a single structure. They act like blueprints for creating objects with specific properties and behaviors. For example, a ball class can have attributes like position, velocity, and methods like move and bounce. We define a class using the class keyword followed by the class name. Inside, we use a special method called init to initialize the object's attributes. Methods inside the class use self keyword to access or modify the object's data. The parameter self is used to refer to the instance of the class itself. So whenever we write a variable within the class as self.position, Python understands that the variable position belongs to the class ball. A key advantage of declaring variables that are part of the class is that these variables can be used and updated by any methods written within the class. Once defined, we can create multiple objects from the class, each with its own unique state. We will build the world object first. The world object has two properties: the location of the ground and the acceleration due to gravity. So the class world would look like this in Python. It has two parameters: ground with a default value of 0 and acceleration underscore gravity with a default value of minus 9.81. Notice that the init function has self as an argument and the ground and acceleration underscore gravity variables are prefixed with the self parameter and a dot operator, indicating that these are members of the class world. Later, we can create an instance of this class like a is equal to world with an parenthesis, and its properties can be accessed like a dot ground and a dot acceleration underscore gravity. The dot parameter indicate that the variables ground and acceleration due to gravity are members of the instance A, which is created from the class world. Now let's create the ball class. This class performs two actions apart from the initialization. So we need to create three functions in total. The ball class is created just like the world class, but the difference lies in the init method, where we pass additional parameters along with self: initial position, acceleration, coefficient of restitution, and time interval. These parameters have default values also, which can be overridden when creating an instance optionally. This allows flexibility for users who may not know all the values upfront. If they don't know, the program uses the default values, and if they need to customize it, they can call the variable names and update their values as required. Inside the init, we assign these variables to the class variables. Self.velocity is set to 0 as the ball is always at rest at the start of the simulation. Self.position gets the initial position, and the rest of the values like self.acceleration, self.dt, and self.coefficient of restitution are assigned from the respective input arguments. This completes the initialization of our ball class. The algorithm for simulating motion of the ball involves three steps, starting from finding the average velocity, updating the position, and then updating the velocity to its final value. These exact steps can be implemented inside our move function. The move function also takes self as an argument. This need not be passed when we call the function, but this shows that the function move is a member of class ball and it has access to variables declared in the class during init function. Thus, we can use variables like self.position and self.velocity inside this function without having to pass them as separate arguments into the function. This shared scope of variables is a powerful feature in classes that allow us to break down complex functions into multiple smaller functions without having to share variables across them each time. To complete the ball class, we need a bounce function. This function is called when the simulation detects the ball has gone below the ground. It does not check for the collision itself. It only defines what happens during the bounce. Again, whether to include the collision check inside or outside this function is up to the person who is developing the model. I chose to keep it outside for better control over bounce, allowing us to decide when to trigger the bounce action without having to modify the ball class itself. The bounce function needs ground also as a parameter along with self. To avoid the ball from getting stuck below the ground due to small velocities, we are resetting the position of the ball to that of ground before reversing the velocity. We assign the variable ground to the class variable position. With the updated position of the ball, we need to reverse the velocity and multiply it using the coefficient of restitution. This completes the implementation of our ball class with an init function, move function, and a bounce function. The primary purpose of an observer is to record the progression of time and the ball's motion during every time step of the simulation. This way, the complete simulation data can be later used for further post-processing. We are recording four parameters here: time, position, velocity, and number of collisions. These can be used to record the information during our simulation. Along with the standard attributes of the observer class, a function to perform post-processing needs to be created to calculate additional parameters like kinetic and potential energy at each time step using the formulas kinetic energy Ke is equal to half mv square and potential energy Pe is equal to mgh. Since the simulation is purely kinematic, we need to assume a mass of 1 kg for the ball to make these calculations. The total energy is simply the sum of kinetic and potential energies. This function runs after the simulation using the stored position and velocity data. Inside the function, we define the mass and create arrays to store energy values. Then we loop through the time array, compute Ke and Pe for each time step, and append them to their respective arrays. Also, we calculate the total energy and append that also. All right, now we have all the required tools to build our simulation steps. Our primary purpose of converting our program into objects and classes was that we can call them inside our simulation loop and use the functions to execute the algorithm without having to code the mathematical operations directly there. So in the same file, we can start the main algorithm. Python will work fine if you just write the steps directly, but a convenient technique is to check whether the file is invoked by the main function call or whether the file is called from another Python script. This is a very important step that is often ignored by beginner programmers. Both approaches are fine if you are writing all your code in a single file and not planning to use the code anywhere else. But for creating a reusable script spanning across multiple files, it is important to understand where the function is getting called. By placing an if condition, like if the name exactly equals main, we are telling the interpreter that it should execute the block inside this if condition only when the file is called by the operating system directly. This means that when we run the file using an IDE or a command prompt. There is another way of consuming the classes in this file. That is by importing the content of this file into other Python files using the import statement. At the start of our code development, we wrote lines like import matplotlib.pyplot as PLT, indicating that we are going to consume the code inside matplotlib library in our code, without having to rewrite any of the graph generating logic. We could just call the plt.plot and plt.show functions to see the graph without knowing any underlying logic of how the graph image is generated. Same way, we can import the files we created into other files for reuse. When we import such a file into another file, the variable name underscore underscore name underscore underscore will be the name of the file instead of main. So it will not trigger the if condition. In short, any code that does not need to be executed when imported to another classes should be enclosed within the if condition of checking the name to main. All right, let's build our simulation now. With all the logical blocks pre-built, our simulation is quite straightforward to implement. We start defining the duration and step interval of our simulation. We will simulate the ball for 20 seconds and provide an interval of 0.01 seconds as discussed in our previous session. Iterations are calculated by dividing the total duration by interval and converting them to the nearest integer. We initiate another variable called time to keep track of the time progression. Next, we create instances of ball, world, and observer classes in our simulation. Remember that the classes we created earlier are just blueprints, and we need to create instances of those classes for actually using them. To indicate that classes are single instances of classes, we can name them a ball, a world, and an observer respectively. Classes are instantiated by providing the name of the instance followed by assignment operator and then the class name. The instances of these classes are also known as objects, and that is where the word object-oriented programming is coming from. Notice that we are passing the initial position of the ball as 10 meters when creating the object. Other parameters like gravity, time interval, and coefficient of restitution have default values, which are used since we are not overriding any of them. This makes it easy to start with a basic simulation and customize it later as we needed to. It keeps the setup simple while allowing flexibility. With the three objects defined, it is time to write our for loop where we will iterate over the time intervals. We create a for loop with for I in range iterations and call the move function inside it. This shows the power of classes. We can run the logic without needing to see the internal details of move. We then check if a ball.position is less than a world.ground to detect collisions. Notice that we are using the dot operator to access class attributes like position and ground. If a collision is detected, we call the ball.bounce method and record the time and position of the collision array. Outside this condition, we log the ball's position and velocity in the observer's arrays. Finally, we update and store the current time in the time array. This completes our simulation loop, and it is clear that this is much cleaner than the previous code, and a person who does not need to understand the mathematics behind the ball's motion can also read this code and understand that we are moving a ball and letting it bounce when we hit the ground. Now, we can call the post-process function from the observer to calculate the potential and kinetic energy. The remaining lines are used for plotting position and velocity and potential and kinetic energy of the ball. We can access the arrays from the observer class using the dot operator. And this completes our entire program. And now let's try to run this code. All right, we are able to see the plots, and it looks like our simulation is running as expected. The first plot shows that the position and velocity. It is seen that the ball takes about 1.42 seconds to reach the ground. Another feature that we did not see in the last video is that plot for velocity. Velocity goes to very high negative values indicating downward motion and suddenly flips to positive indicating the bounce. These flips exactly coincide with the point where the ball hits the ground, ensuring the physical consistency of our model. The next plot shows potential and kinetic energy and total energy. The potential energy follows a similar curve as the position because it is proportional to the position of the ball. Kinetic energy is maximum when the ball hits the ground and zero when the ball reaches the maximum height. Also, we can see that the energy of the ball is decreasing after each bounce. Now, we have the models ready for simulation and we have tested them for results. Let's see how we can consume the existing simulation classes in a real-time animation script using Pygame. Pygame is a Python graphics library primarily designed for 2D game development, but it is also quite good for simulation visualizations. It allows users to create graphic objects such as circles, rectangles, and control their position, color, and size using variables. It also has advanced features to capture mouse location, keyboard inputs, and make the its animations more interactive. We will learn these concepts when we develop more advanced simulations, but for now, the intention is to briefly walk you over the Pygame code and show how easy it is to use our simulation in an external environment like Pygame. For using Pygame, we need to import the Pygame module and sys module into our code. Sys module is used to exit the application smoothly as programs with graphical interface will be running in an infinite loop and we need to click the close button of the window to stop the execution. GUI programming, also called event-driven programming, is a bit different from our conventional understanding of computer programs that consume some input at the beginning and produce an output at the end. We import the bouncing ball class as BB, which is the file where we were previously working on. It is important that both files should reside in the same folder for this import statement to work for the custom files that we create. If we are importing a system library like sys or matplotlib, their path will be already known to the Python interpreter and they can be imported without specifying any path. And the as bb is an alias that is given to the file name so that we don't need to type the full file name inside our code wherever we call the classes from this, but we can only call them as bb. This is just a step for conveniently writing our code, avoiding large file names. Then we create a class called user interface to build our code within the init function. Again, depending on the complexity, this can be further split into more functions. But for now, most of our code can be handled by the init function itself. For a visualization, we start by defining the size of our window as 800 by 600 pixels and provide a caption to the app. We define the key colors using their RGB coordinates. Then we define the properties of the circle that will represent our ball. Also, we define properties of a horizontal line that will act as the ground. Notice that we are creating these positions with respect to the size of the window so that complete animation can be captured within the visible region of the window. Next, we create the instances of our ball and world classes that will be used for running the simulation in this code. Note that we are not importing the observer class because we are not planning to create plots, but rather we are trying to simulate the ball motion with a real-time animation. We will create two instances of ball and see how simulation varies when we change the acceleration and coefficient of restitution of each ball. We call them by using the dot operator because the ball class and world class are defined within the BB, that is the bouncing ball class. We provide 10 as the initial height of the ball and 0.85 as the coefficient of restitution. Next, we create a conversion factor that will translate the physical units of the ball's position in meters to the respective pixel dimensions on the screen. Pygame considers the top left corner of the window as the origin of its coordinate system and the bottom right as the 800 by 600th pixel of the screen. This factor is the ratio of the pixel coordinate distance between the ground line and the center of the circle and the ball's actual height from the ground. We will also create some font and text to indicate the time and the position of the ball on screen. We start the animation sequence using a while loop. Notice that instead of giving a fixed number of iterations, the while loop runs for an infinite time with the condition given as while true. Within the while loop, we have the option to kill the loop using the close button as we mentioned earlier. There we are using the sys module to call the system exit function. Next step, we call the move function of both the balls and check for collisions with the ground for each of them. We have to handle the collision checks separately because both balls will be hitting the ground at different iterations. If it detects a collision, we will call the bounce method. Then we pass the position of each ball to draw the circle function of Pygame to draw the balls on screen. Rest of the code mainly deals with the process of drawing the circle and ground line on the screen by using a conversion factor. An important point to note here is the clock.tick method. We created a clock instance at the start of the program, and this will control the frame rate of our animation. As we are using 0.01 second as the time interval of simulation, it takes 100 iterations to cover 1 second of time. So we need to run 100 frames per second to get a realistic feel of the bouncing motion. Then we invoke the instance of classes using the if name equals main condition to start the simulation. Let's run the simulation and see how nicely the ball is moving across the screen based on our algorithm. At this point, both balls are identical and they bounce exactly the same way. Now let's double the acceleration of our second ball and see how it affects our simulation. Let's change the default value of g in the second ball and rerun the simulation. Now with increased acceleration, the black ball falls faster than the blue one. Now let's try another scenario by changing the coefficient of restitution of the blue ball. For comparison, we will reset the acceleration of both balls to default and change the E value of the first ball to 0.5 instead of the default 0.85. Let's rerun the simulation. As we can see, now the blue ball drops height much faster than the black ball after every bounce, and it comes to rest much faster than the other one. So this shows the potential of our simulation, how we can control our simulation parameters without actually having to tweak the algorithm. And this offers a large window to experiment with different parameters and understand how the ball behaves under different circumstances. So there are a lot of different studies that can be performed using these simulation models, like how fast does the energy decay occur with a change in coefficient of restitution? How does the initial position affect the time it takes for a ball to stop bouncing? What will happen when the acceleration is set to very small values, and so on and so on. I leave it to you to explore such possibilities after building your own code and understand more details about the motion with uniform acceleration. This concludes today's session on how a simple simulation of a bouncing ball can be created using functions and classes. We also learned how a simulation model can be imported into another file for consumption. We also understood the basic overview of event-driven programming using Python and Pygame. Don't worry if you could not grasp the full extent of the Pygame usage in this video. I will try to do a separate video explaining the basic concepts of Pygame, or you can check their official website or other tutorials for more details. In the next session, we will see how we can describe the motion of objects in 2 dimensions and try to simulate projectile motions. There are a lot of new libraries like NumPy, which offers very powerful tool to perform numerical computations in Python that we will come to know during the next sessions. And I truly appreciate your interest in computer simulations and physics and for sticking with me for this long. Please let me know your comments, suggestions about the video in the comment section. Also, do subscribe to the channel to get notified on next updates. Till we meet again, goodbye.